Gas turbines power aircraft and generate electricity. At their core lies the axial flow compressor. Its performance dictates the efficiency and power output of the gas turbine. The compressor draws in and compresses large quantities of air. This compressed air is fed into the combustor, where fuel is added and ignited. The resulting hot gas expands through the turbine, driving the compressor and output shaft. Axial flow compressors handle large airflow volumes and achieve high pressure ratios. They compress air with minimal energy loss, making them essential for high-power applications. Modern compressors achieve high adiabatic efficiency. These characteristics make the axial compressor the heart of large gas turbine engines. The relentless pursuit of better compressor technology drives innovation in aerospace and energy sectors. Each new generation of design becomes more efficient and capable. Gas dynamics is the science of air in motion, crucial for compressor design. Engineers use these principles to predict air behavior through the compressor. This involves analyzing changes in pressure, temperature, velocity, and density. Managing airflow precisely at each stage ensures smooth and efficient compression. At high speeds, air behaves as a compressible fluid, changing density as it is compressed. Ignoring compressibility can lead to inefficient operation or failure. The Mach number, representing flow velocity to the speed of sound, is key in compressible flow. Airflow can be subsonic, transonic, or supersonic, each presenting unique challenges. Shockwaves in transonic and supersonic flows can cause aerodynamic losses. Engineers use computational fluid dynamics, CFD, tools to simulate and optimize airflow. This iterative process helps create powerful and efficient compressors. The objective is to achieve the desired pressure rise with minimal losses. The principles of gas dynamics guide the shaping of compressor aerofoils and flow paths. This ensures stability and efficiency in the aerodynamic design of blades and vanes. Axial compressors achieve high pressure ratios through multiple stages. Each stage consists of rotating blades followed by stationary vanes. The air flows axially through these alternating rows. Rotor blades accelerate the incoming air, increasing its kinetic energy. Stator vanes decelerate the air, converting kinetic energy into static pressure. This combination forms a single compressor stage. Multiple stages in sequence achieve high overall pressure ratios. The air passes from one stage to the next, steadily increasing in pressure. This multi-stage architecture is fundamental to axial compressor success. It delivers continuous, high-volume, high-pressure airflow. This is essential for efficient gas turbine operation across various applications. Compressor blades are sophisticated aerofoils, optimized for airflow. Their shape controls airflow smoothly, maximizing pressure rise and minimizing losses. Materials must be strong, lightweight, and withstand high temperatures. Blade height decreases from front to rear stages as air density increases. The annulus cross-sectional area decreases to maintain optimal axial velocity. Tip clearance must be minimized to reduce leakage and maintain efficiency. Advanced sealing technologies manage tight tolerances, ensuring performance and reliability. Compressing air raises its temperature significantly. This hot air is delivered to the combustor for efficient combustion. Bleed air is extracted from the compressor for turbine cooling and other functions. Cooling high-pressure turbine components allows higher inlet temperatures. This boosts engine power output and thermal efficiency. Bleed air extraction imposes a performance penalty on the compressor. Designers minimize bleed air requirements with effective cooling schemes. Optimizing the bleed air system is crucial for high performance and efficiency. This balance is essential for modern gas turbine engines. The compressor shaft transmits power from the turbine to the rotor assembly. It must be strong, stiff, and lightweight to withstand torsional loads and prevent vibration. Multi-spool engines use concentric shafts rotating at different speeds. Materials like titanium alloys and nickel-based superalloys are used for strength and temperature resistance. Bearings support rotating shafts, allowing high-speed operation under substantial loads. Effective sealing prevents air leakage, maintaining efficiency and performance. Labyrinth and brush seals minimize leakage without direct rubbing contact. Advanced materials and designs improve performance and reliability. Composite materials are being introduced for further weight reduction. Bearings must be lubricated and cooled for long life and reliable operation. The design and placement of bearings manage dynamic behavior and prevent issues. Minimizing leakage is crucial for overall engine efficiency. Inlet air conditions significantly impact compressor performance. Denser inlet air improves performance by increasing mass flow and pressure ratios. Inlet air cooling techniques like evaporative coolers and fogging systems enhance performance. Inlet air filtration protects against foreign objects that cause erosion and damage. Moisturizing inlet air can enhance performance by cooling and increasing mass flow. Techniques like high-pressure fogging or direct water injection provide intercooling effects. This reduces compression work, increasing pressure ratio and efficiency. Careful control of water injection avoids blade erosion. Managing inlet air conditions optimizes gas turbine operation. This is especially valuable for stationary power generation units. Modern gas turbines use sophisticated control systems for optimal performance. These systems manage airflow to maintain stability and efficiency. Variable stator vanes, VSVs, adjust angles to optimize airflow incidence. Active stall and surge control systems prevent instabilities. Full Authority Digital Engine Control, FADEC, integrates all control functions. FADEC optimizes performance, fuel efficiency, and component life. It provides diagnostic information for safe and reliable operation. Advanced controls push the boundaries of compressor performance. They ensure high levels of performance under diverse conditions. The demand for efficient, cleaner, and quieter systems drives compressor innovation. Future advancements aim to improve fuel consumption, reduce emissions, and mitigate noise. Advanced materials like ceramic matrix composites offer higher temperatures and reduced weight. Computational fluid dynamics, CFD, enables more aggressive aerodynamic designs. Novel architectures like counter-rotating spools improve efficiency. Boundary layer ingestion, BLI, offers vehicle efficiency benefits. Integration with hybrid electric systems presents new challenges and opportunities. Innovations in aerodynamics, materials, and control systems drive evolution. Advanced compressors enable sustainable aviation and efficient power generation. This technology addresses global challenges for a sustainable future.